Okay, so good morning to everybody, and thank you to the organizer for having me here. It's my first time here in Santa Barbara, and I'm enjoying very much the conference. So I'm going to talk about reionization. There were already yesterday the very nice talk by Benedetta, today talk by Martin, there will be other talks after me discussing this topic. I would like, first of all, to make a point, since there are a lot of people working on with JWST data here. So, of course, if we want to understand the reionization process, we, of course, need these very nice galaxies to study them, understand their properties. But we also need the complementary information regarding the gas that is surrounding these galaxies. And we get this information mostly, I would say, with the bright background quasars that we observe from the ground spectroscopically. So as Martin was mentioning before, the first quasar redshift larger than 6 have been found by the group of FAN in the Sloan Digital Sky Survey. And here you see the very famous picture with the 19 quasars that were in the Sloan. Going from redshift 5.7 to redshift 6.4, that already were showing how the Lyman alpha forest was evolving from this redshift to the very high redshift where it was really completely absorbed. And what you can do is, of course, to study more quantitatively this evolution of the absorbed flux is to use the effective optical depth that is here defined as the minus the natural logarithm of the transmitted flux. And so what was seen with this first sample was that the behavior of the average value of tau was evolving similarly to lower redshift up to redshift 6, and then there was this upturn that was interpreted as to be due to the final phases of reionization when the overlap phases was happening. So the number of quasars above redshift 6 has really dramatically increased in recent times. So we went from the 10 objects that were in the first review by FAN to the almost 300 that are known now. And this increase has happened more or less in the last, maybe in the last 10 years, in fact, thanks to new photometric surveys. So this large increase in the number of discovered objects above redshift 6 was what motivated, let's say, the community working on this topic to try to collect a statistically significant sample of high-quality spectra of these objects in order to carry out all the science cases that can be, in fact, studied with good quality spectra of high redshift quasars. And this sample is called XQR30 because there are 30 objects that have been that were selected and observed with the X-shooter spectrograph at the VLT. But then, thanks to also other 12 objects that were already present in the X-shooter archive, the sample is now formed by 42 objects, and you can see it here in this plane where there is the resolving power here, and the median signal-to-noise ratio per 10 km per second pixel, and also the number of objects in the sample compared with other samples, homogeneous samples, let's say, coming from different instruments. So you can already see from here that this is really an extremely good quality sample that have been used in the recent, let's say, 4 years to obtain a lot of nice results. And I will try to highlight, let's say, a selection of these results in my next slides. Here I'm showing also an example, 2 examples of at least the visual part of the spectra, and you already see how the resolution, the signal-to-noise ratio of these objects are really great, and you see how the big difference that you have going from redshift 5.8 to 6.5, whereas here you see a lot of these transmission spikes that were mentioned also before, and while here you see, for example, this very long, completely absorbed trough. So first of all, of course, this sample had been used to study the process of reionization using the Lyman alpha and Lyman beta forests. And as already Martin also was mentioning, of course we can study the average values of this optical depth, but maybe it is more informative to study how this optical depth is fluctuating, let's say, along different lines of sight at the same redshift. And this work was carried out by Sarah Bosman. Here I'm showing, so the work in fact was based on an even larger sample based on X230, but also with other quasar of good quality. Given the high quality of the spectra, she could use in fact very small beams of redshift of 0.1, and she analyzed the redshift range between 5 and 6.1. Here in this figure, I'm showing you this cumulative distribution function of the optical depth, which are the observed one is these black lines that you see, compared with simulations in which, however, the UV background is homogeneous. So this simulation in particular are the Sherwood and the Nix simulations. And Bosman and collaborators, they compared let's say they forward model the observation with the simulation and derived this probability distribution function for the most likely value of the optical depth, while here the black line is the observed value. And what you can see is that while at redshift between 5 and 5.2, these values are in good agreement, at redshift 5.3, they start to be in mild disagreement. This is a standard deviation of about 2.5. And above redshift 5.4, there is a very strong disagreement between the observation and the simulation with the homogeneous UV background. So this is telling us that, of course, an homogeneous UV background is not explaining well this observation, and it is can be let's say an evidence of the fact that there is still reionization ongoing at this lower redshift. I mean, and the other statistics that have been used was the statistic of the dark gaps, where, as I was mentioning before, a dark gap is a region in the spectrum in which the transmitted flux is lower than a given threshold that, of course, is decided a bit arbitrarily when measured in beams of a given length. And here, let's say the analysis of these dark gaps in this sample of objects were carried out by Yongda Zhu, who was a PhD student of George Becker. And here you see the dark gaps with a length larger than 30 megaparsec in the sample, and it is already extremely interesting to see how many of these dark gaps are present below redshift of 6. Here I've marked redshift of 6. When you do a more quantitative, let's say, comparison and estimate of the number of these dark gaps, and you compare with simulations, in particular here, I'm showing a comparison between the dark gaps in the Lyman beta forest, because what happens is that, of course, the Lyman beta forest is more constraining than the Lyman alpha forest in terms of the darkness, let's say, of the absorption, because it is less sensitive to the presence of the neutral gas. So you get stronger constraint considering both the Lyman alpha and the Lyman beta forest. So here you have in green the number of dark gaps with a length larger than, sorry, I wrote less than, but it is more than 10 megaparsec at redshift below 5.8, compared with what you derive from different simulations. So here again you have a simulation with a homogeneous UV background, and you see that with the homogeneous UV background it is not possible to reproduce the data. Again, here you have a simulation in which, by Laura Keating in 2020, in which the, let's say, midpoint of reionization is at a redshift 8.2, and again, such a, let's say, early reionization is not in agreement with observation, while these two simulations, again by Laura, where you have a late reionization and you are distinguishing, let's say, more subtle differences between the simulation, they are in agreement with at least, I mean, they can be considered in agreement with observation, but it is difficult to distinguish between subtle differences in the simulation. Another point that Martin mentioned very rapidly, and I'd like to instead show you a bit in more detail, is the fact that, of course, if we think that these long dark gaps are due to neutral islands in the IgM, we could expect to see damping wings in the red border, let's say, of the dark gap. And this is, in fact, what George found in one of the most famous, let's say, dark gap, because it is the largest dark gap at redshift less than 6 in a spectrum with a very high signal-to-noise ratio. And you can see here in the Lyman alpha forest the red, let's say, limit of this dark gap, which is fitted very well with the damping wing. And let's say that the explanation of this dark gap as a neutral island instead of, for example, a damped system is preferable because there is no observation of metal lines in this case, and so the scenario that could be here also you see that this is the redshift, initial redshift of the quasar. So the scenario could be that the quasar, of course, is ionizing its proximity region, but probably you need to have also other galaxies that are contributing to the ionization in this region, because otherwise, I mean, you're not explaining such a long transmission region. And then you have the line of sight impacting on this neutral island that give rise to the very long trough that we are observing in the spectrum. And what Yongda did was also to try to find the evidence of damping wind by stacking all the dark gaps in the large sample that he analyzed, and found a possible evidence in the stacking also of a damping wing that would imply a neutral fraction of hydrogen larger than 6.1 at 5.8, again pointing to a ionization that extends below redshift 6. Another quantity that you can measure from quasar spectra is the mean free path. That is the distance that ionizing photons can travel before being attenuated by a certain factor, which is adopted as 1 over E. And so you can measure this length in different methods. So what Yongda did was to measure it directly from the spectrum by stacking spectra at different redshift and obtaining these red squares that you see here. So what you see, and maybe I put it a bit small, but here is you see better the evolution with redshift. So here you're going from redshift 2.5 to redshift 6. And while you see that the evolution before redshift of about 5.3, 5.5 is smooth and following, let's say, the natural evolution that you can also derive theoretically, above redshift 5.5, you see a very rapid decrease in the size of this mean free path, which again goes into the direction of, let's say, a final phase of reionization happening at this redshift. So this is a selection, as I said, of the results concerning the Lyman alpha forest. But of course, in this XQR30 spectra, we not only have information on the Lyman alpha. In fact, the information on the Lyman alpha is becoming, let's say, less and less important as you go to higher redshift, because everything is absorbed. But you have also all the red part of the spectrum, where you have a lot also of metal absorption lines. And so part, of course, of the work that was carried out on this sample was to study the metal lines and how they evolve at this very high redshift. So, of course, some work was done also before this this sample was collected, and in fact already something that has was found already with the first samples of high redshift quasar was this very rapid increase in the carbon-4 number density at redshift between 6 and 5. So here you see the rapid increase in carbon-4 and also in silicon-4. This was initially explained as due in particular to the increase in the metallicity that was rapidly, let's say, increasing due to a very strong sun formation at those epochs. But then in 2019, George Becker analyzed the number density of neutral oxygen, and he found that, in fact, neutral oxygen has a completely different behavior. So what happens is that neutral oxygen is decreasing from redshift 6 to redshift 5, and then possibly increase again at lower redshift. So when you put together the information from the different ions, the picture that comes out is that at least part of this evolution is due to the ionization state of the gas. So also this is giving you not just information on how the metal enrichment evolves, but also on how the ionization state of the gas evolves. So now with the XPR30 sample, of course, the number of lines has increased really at least by a factor of 4. And the catalog of lines was, the work for the catalog lines was led by Rebecca Davis, who was a postdoc of Emma Ryan Weber in Australia. And here you see a summary of the absorption lines that are found in the sample. So here is a pictorial image, let's say, of the lines with the different main ions, so magnesium 2, iron 2, carbon 4, silicon 4, C+, and nitrogen 5, and how the redshift range which is covered, and the ionization energy of the different ions. And here you see, in a more quantitative way, let's say, the number of lines that we have for the different ions and in the different redshift range. In particular, we have almost 480 carbon-4 systems, of which about half are above redshift of 5. So of course we can again, let's say, carry out the same measurement that we did with the previous samples, but using a smaller redshift bins and of course having a much smaller error bars in determination. Still, of course, we see, if you look at the solid pentagons here, you see a very steep rise of the carbon-4 number density and then a flattening at lower redshift, the possible increase again at the redshift of about 2. It is really difficult to explain this behavior with models, so up to now there are no models that are able to explain the whole behavior, let's say, in particular of carbon-4. You see here, for example, a prediction by Christian Finlater model where it's underproducing, let's say, the carbon-4 here. You can boost the carbon-4 by a factor of 1.75 to explain the rise, but then you are over-predicting the carbon-4 at this lower redshift. So still we need, there is the need to work more on the models to try and explain this behavior, in particular considering different ions, of course, not just the carbon. So thanks to this sample, it was possible to study also carbon-2 in this case, and it was, I think, very nice to see that carbon-2 behaves like oxygen. So it decreases between 6 and 5. And this could be expected, of course, if the behavior that we were seeing for oxygen was due to the different change in the ionization state of the gas. What is also interesting is that when you put together the information from carbon-2 and carbon-4, in particular in the cosmic mass density, you see that they compensate very well in the redshift range in which you have both measurement. So I think this is interesting because, of course, for simulation, it is probably easier to reproduce the total amount of carbon. Of course, if you want to have the ions, you introduce more uncertainties. And so we are going, let's say, at least in the direction of maybe having a better or easier way to compare with simulation. Unfortunately, for the moment, we don't have information on this in this redshift range for carbon-2, but this is something that, I mean, the data are available. I think it's just something that we need to do. I mean, what instead will not be possible to obtain is the information on carbon-3, which is another ionization state that at lower redshift, for example, in which you see a lot of carbon, but unfortunately the main transition is in the Lyman alpha forest, and so we cannot observe it in particular in the high redshift where the Lyman alpha forest is completely absorbed. And again, in this work by Alma Sebastian, where she studied also the carbon-2, she also recomputed also the evolution of the neutral oxygen for the EXPR30. And if you look at the light blue points, you see again the rise that was seen in the work by George previously. So we are confirming this this behavior. But the neutral oxygen systems are also interesting because they can trace the neutral hydrogen gas. So we can use them as tracer of the damped Lyman alpha systems that also Stefania was mentioning today. Unfortunately, at this redshift, we cannot. We only have the neutral oxygen. We don't have the. We can, let's say, rarely can measure the neutral hydrogen, but we can make the hypothesis that these oxygen systems are damped Lyman alpha systems. And this is confirmed in those cases in which the system happens close to the quasar, and we can, in fact, see the damping wing and fit the absorption. Another hypothesis that we make to analyze these systems in terms of chemical abundances is that they are metal poor, that is, they have a metallicity lower than at least 100 solar. And this, I mean, is an hypothesis, of course, but that goes in the direction of the observation at redshift 5, where you see that most of the DLAs, in fact, where you could measure the H1 had such a low metallicity. So what we did was to study a large sample of neutral oxygen systems at redshift larger than 5.4, study their chemical abundances, and compare with what we see at lower redshift in order to, first of all, in order to see if we could find some signature of POP3 enrichment in single systems, but also to see if there were some changes, statistical changes, let's say, comparing with the lower redshift population. And here you see the comparison of some chemical abundances, silicon of the iron and oxygen of the iron, as a function of redshift for this sample, which is represented by the red point here, and the lower sample of DLAs at metal poor DLAs. What happens is that for all abundances above redshift of 5.5, there is an increase in the scatter of the chemical abundances. And so what we did was to compare then these observations with the prediction of different models that were predicting the abundances of POP3 stars, in particular comparing with the simple models by Kulkarni and the models by Ma et al. 2017. We could exclude enrichment from peninstability supernova from these systems, while comparing with the prediction of the parametric model by Vanni that was described by Stefania before, what we see is that an increase in the dispersion is exactly what we expect when there is at least a contribution, let's say, to the abundances due to POP3 stars. And we see this in this space, but we see this also in the space of, let's say, abundance versus abundance. And in particular, we have these three systems which are really going in the region enriched by POP3 stars, which are these, I mean, purple, pink, and yellow regions, while the regions enriched only by POP2 stars are these gray regions, which are due to two different sets of yields. So I think this is also something very, I mean, Of course, you have to rely on the yields that are available today, but I think this is also a nice indication that maybe not on single systems, but in a statistical sense, we are seeing some signature of the enrichment, of the relic enrichment from pop-3 stars. How much time do I have still? Okay, so just, very rapidly, I wanted to at least say something on the synergy. There is a lot of synergy, in fact, between JWST, of course, and these kind of studies, because with JWST, you can identify the galaxies in the field of quasars, and then you can then cross-correlate galaxies with the absorption that you see in the spectra. There are now at least 3 works that have done that with JWST data. So the first work is the one by Cascino et al. From the Eiger survey, which is going really very deep in the field of a small number of high-redshift quasars. But already, from this field, they obtain a lot of results. I think Christina also will present something related to this field. And here what of course, here what you see are the galaxies, which are these squares and dots, and these triangles are the absorbers, where the magenta triangles are the carbon-4 absorbers. And this field is confirming a previous result obtained with the MUSE spectrograph in the field of the J1030, which is a famous 6.3 quasar that was studied, whose field was studied a lot. That is that for all carbon-4 systems with a column density larger than 13.5, you always find the galaxy within 200 physical kiloparsecs. So this is confirmed by this field. I'm really looking forward to other fields that will analyze this correlation. I think, of course, you can do much more quantitative and maybe detailed studies to study this, but still I think there is time to do it. And another, I think, the last point that I want to make is that, of course, you can also cross-correlate galaxies with the flux in the Lyman-alpha forest to see if you can see an effect of the galaxies which are close to the line of sight in terms of ionization of the surrounding medium. So in principle, you would expect that if the galaxies are ionizing their surrounding medium, you should see a transmission spike when you have a galaxy which is close to the line of sight. This is what was also done by Cascino in this paper, and this is the result that he obtained. So you see, in fact, there is an absorption up to about 5 megaparsec, and then a transmission at larger distances. This was compared with simulation, the TESA simulation, which find slightly different, I would say, results. So this is also something that, of course, has been done just in one field, but that can be done in all the other fields. There are also another program which is a SPY, which is a bit less deep, let's say, than Eiger, but it also are slitter spectroscopy with JWST in fields of high-redshift quasar. So just one point that also Martin skipped before. I mean, we are a bit at the limit, let's say, of these kind of studies, because redshift above 6, above 7 quasars are really faint. And already with the shooter, we had to observe them for 10 hours at least to have a decent spectrum. So really the next big step will be represented by ELTs, and in particular, I'm involved in the high-resolution spectra for the European ELT, which is called Andes. So I think this will make a big difference. And so I go back to my results, and thank you.
Okay, thank you very much, Valentina. Questions? So yes, Alice.
Thanks so much for such a wonderful talk. That was really great. I have a question about the evidence for population 3 enrichment in the absorbers, where you have the confidence intervals. So it looks to me like in most of the panels, it looks like there's evidence for significant population 3 absorption, but not in the upper right with the silicon to carbon and carbon to iron, where it looks like it's pretty consistent with mainly population 2 enrichment. So how do you interpret the full ensemble of the plots then?
So I mean, of course, the yellow is not just in the external part, so the yellow is everywhere. So there is this confusion region that Stefania was mentioning before. So there are some abundances which are more, let's say, significant than others, are more useful than others to identify this POP3 enrichment. But also in this case, I mean, the yellow, which is a 100% or 90% POP3 enrichment, is also in this region, in fact. So just a matter, let's say, of finding the best abundance that can give you really the correct answer, which is not always easy with these objects, because, for example, zinc is very hard to measure in this spectra, while it would be a very important element, for example, to measure.
Thanks.
Other questions? Okay, so let's go like this. So.
Hi, yeah, also on this point of here. So I guess maybe a question about, are there other elements that you can get out of these? In particular, I guess, all of these elements are extremely affected by sort of the assumptions of the core collapse supernova for POP2. So are there other things like aluminum or something that you can?
So aluminum, yes, we have it for some of the systems. Not for all of them, but in general we can put good upper limits. Yeah. Aluminum, I would say, not many other elements.
Yeah.
Nitrogen?
And magnesium, nitrogen, no.
Yeah, and then maybe quickly something else. So these are metal poor. How likely is it that there's some sort of gas inflow that makes them metal poor, if that makes sense?
No, this I cannot answer. I mean, really, of course, there is the possibility. This is, diffuse gas. So of course, there is the possibility that they have been also. The metallicity. Let's say, of course, we are not measuring directly the metallicity because we don't have the H1.
Okay.
So it's an hypothesis that we make based on what we see at lower redshift in the general population of the LAs. Let's say.
I see. Thank you.
Let's say when we measure the H1, they are metal poor.
So thank you, Vale, for this beautiful talk. So I was curious to know how you account for the possible depletion on dust, because when you look at the stars,
no, of course. So
you are okay.
Because we make this, this hypothesis that they are metal poor, we are not accounting for dust depletion. In fact, this is something also that. Having probably with Andes more elements, it will be possible to maybe at least check.
Very nice talk. Back to that plot again with the POP3.
Yeah, shouldn't have been
not
in
this
the
one, the
focus
other
of the
one,
talk.
the one with the
other one.
various ratios, yeah.
Yeah.
Yes. So there is a source, if you look at the silicon to carbon and oxygen in the fourth bottom panel, right, that appears to be only in the outer.
This one?
Yes, yeah. So obviously that source is there in all the other plots, and it's not an outlier. So how does one interpret that? That is just an anomalous ratio, because it's not self-consistently sitting
it is here,
the predominant.
It is here.
Yeah.
It is here. So this is the plot where it is not, let's say, in such an external region. I mean, it's hard to tell. I have to say. I mean, also because I'm not doing the model. So.
An outlier in one of these spaces doesn't have necessarily to be the same in another space. So
it's very hard to interpret in a coherent way. Okay, thanks.
Okay, other questions? No, so I think I can ask one question. So you showed in one of the previous slides about the carbon absorbers, like in simulations and observations, and there was this mismatch, right? So do you have an idea of like what could be causing this? Like what are we missing in the simulation? So is it due to uncertain metal yields, or the way the metals are like, spread out by stellar feedback into the CGM?
So I think probably there is a combination of problems. For example, the carbon-4 has also the defect, let's say, that the ionization potential falls where there is the helium-2 jump in the UV background. So this is really a region where the also UV spectrum is very uncertain. And so there is this further, let's say, uncertainty. Silicon-4, for example, is simpler, and also the same simulation by Christian are reproducing Silicon-4 better. Okay. But there is then a problem of size of the simulation. The simulation here, for example, by Christian are not very big, but instead to reproduce, for example, the high column density absorbers, you need quite a large volume. So I think there are several factors that combine together. Then, of course, I mean, as also Benedetta was saying yesterday, the feedback that we put in simulation is not constrained, very well constrained, so we don't know precisely if how these metals are distributed is, in the correct way or not. So I think there are really a lot of but I think that using several elements together, or this maybe can also constrain more simulation and give us anyway more information.
Yeah, absolutely. So are there other simulations planned, or is Christian planning to do some modifications?
I don't know if Christian is, I think so. I think they are working, but carbon-4 is really hard.
Okay, I see.
There are, I think, also other plans, yes, but having metals in simulation is not so easy.
Okay, are there other questions? Yes.
You showed that you can actually estimate the total carbon abundance now, at least for
carbon-2 plus carbon-4, let's say.
So for at least a small fraction of this redshift range. Yes. And how do the simulations compare with that? Because this would be a way to...
No, we didn't try. We didn't check in the paper. But yes, that could be also a good test to do.
Martin has another question. Just very quickly, because we are running out of time, but perhaps if you can just go there. Yeah, thank you.
I just wanted to briefly comment on this. So there are two issues here. The one is the high incident rate. And this is, in most simulations, the volume filling factor of carbon isn't large enough. This you would have to deal with the feedback with. Laura Keating had a nice paper in 2016 looking at it. The other thing is this very rapid evolution, where it's very helpful to know that the overall carbon doesn't change. So this probably has to do with the UV background that is changing, and it's sort of it's tempting to blame it on helium-2 reionization, where you could have some early helium-2 reionization, which leads to a rapid change of the spectrum.
Yeah, I didn't have the time in this talk to present the results by Laura, who made a very nice comparison, in fact, changing different things and trying to reproduce the data. And I think that, of course, this kind of studies should be done maybe with the new data and see what we get.
Okay, thank you. So I think we can stop here. Let's thank again Valentina for the great talk.